Hi, my name is QISTINA. I will explain an introduction of this project. So, according to the Jabatan Perkhidmatan Veterina Malaysia, Malaysia is estimated with 3 million animals in population, and the swine itself is recorded with 1,618,000 in the year of 2018. And the livestock farming waste causes significant pollution and water sources. Thus, the Department of Veterinary Service (DVS) has come up with many initiatives to reduce the environment issues. One of the most profitable and environmental friendly way is to dispose the livestock farm waste to biogas. Biogas plant can produce green energy resource to reduce the uses of the fossil fuels. Moving on to the problem statement, there are too many pigs farmed in Malaysia and most of the swine farm waste are poorly managed, and that can be cause air and water resources pollution. The VS finds ways to dispose of the pig farm waste in the cleaner, efficient and economical method in order to produce biogas from anaerobic digestions of pig manure to overcome the issues. For the objective of the project, the main aim of the project is to design a fully operational biogas production plant which to convert pig manure into biogas and biofertilizer. There are 6 objectives that needed to be achieved, which are to optimize the feedstock conversion, to design the separate system, to achieve zero waste management, to equip the essential safety features in biogas plant, to minimize the energy consumption and to provide the most efficient plant with high return of investment.
Hello, I am SHALLU KRISHNAN and I will be beginning my presentation with the site location feasibility. So prior to selecting a plant site location, it is crucial to conduct a feasible study to guarantee a convenient operation run with maximized profit and minimized total cost. So we have named a few selection criteria that we find important for our plant site. Firstly is the raw material availability, which will be mostly pig manure. Secondly, the product market proximity for our products biogas and biofertilizers. And for transportation facilities, water supply, labor supply, flood and fire protection, and community factors. So we have selected 3 locations throughout Peninsular Malaysia, which are Tanjung Sepat Selangor, Segari Lumut Perak, Seberang Perai Selatan Penang. So out of these 3, we find that Tanjung Sepat Selangor will be the most suitable with the highest score in the scoring matrix. This is because Tanjung Sepat holds the largest pig farming area in Malaysia with approximately 250,000 pigs. And it is located in the center of Peninsular Malaysia in Selangor with better infrastructures for transportations, water supply, and flood protections. The market is also close with the Klang port being just 1 hour away and the site being located over the National Gas Malaysia supply grid. Hence, Tanjung Sepat Selangor was selected to be the site location for our plant. This is a look over the Malaysian supply grid with our site selections here. The first marker here is the Pulau Pinang, and this will be the Segari Lumut, and this is Selangor. As you can see, Selangor is very convenient with other facilities around it, and it's located over the supply grid and surrounded by independent power stations which will be making use of the biogas. Hence, Tanjung Sepat Selangor was selected to be the best location for our plant site.
My name is Gauzen Teo, and for my first part of my presentation, I will be presenting on the process screening under the chapter Conceptual Design Analysis. This will be the first process route alternative, where we will have 4 major equipments, which is 2 anaerobic digester, 1 admin scrubber, and 1 liquid solid separator. For the second alternative, we will have 2 water scrubbers, 1 anaerobic digester, and 1 liquid solid separator. And for the last alternative, we will have 5 major equipments, 2 anaerobic digesters, 2 water scrubbers, and 1 liquid solid separator. So this will be the summary of major equipment for each alternative. If you compare the first alternative with the other 2, We can see that the difference is the use of admin scrubber. And from our studies, we have found that admin solvent used in admin scrubber is more expensive compared to water scrubbers. And besides that, the regeneration of admin is complex and requires more processes and equipments. And also because the admin is more hazardous compared to water, and our group has also agreed not to waste too much resources on the treatment of wastewater, so we decided to eliminate this first alternative. Now, comparing the second and third alternative, the difference is only at the number of digesters used. The third alternative uses 2 digesters, whereas the second alternative uses only 1. And from our literature review and studies, we have found that multiple digesters provide more benefits in the production of biogas. Basically, there are 4 main chemical processes in the production of biogas, which is hydrolysis, acetogenesis, and methanogenesis. And for the third alternative, we have 2 digesters. So for the first digester, we will be able to put the first 3 stages, which is hydrolysis, acetogenesis, and acetogenesis, with a lower hydraulic retention time. And the products from the first digester will go to the second digester, where there will be the last stage, which is the methanogenesis taking place. And we want a higher retention time for methanogenesis because that is the final stage where most of our biogas is produced. And so by having a higher hydraulic retention time, we will also have a higher methane yield.
Hello, my name is Tan Hao. So let us start with the feed composition for inlet. So for the inlet, we are using pig manure and sawdust. So the table here shows the composition of pig manure and sawdust and all the information we obtained through literature review as well as some information from online website. And then initially the CN ratio for pig manure is quite low. It's just around 20 something. That's why we are doing the cold digestions with sawdust. And then we are doing for wet digestions, which is referring to 20% of TS, total solid percentage, or lower than 20%. So in order to achieve same ratio of 30 and also 20% for our total solid percentage, after some basic mathematical calculations, the flow rate of sawdust, pig manure and water are listed at table below, which is pig manure is around 1000 kg per hour, sawdust is 1500 kg per hour, and the water will be around 6500 kg per hour. They're going to be our inlet. And then actually the biogas that produce depends on the amount of biomass that we have in our inlet. The biomass is referring to carbohydrates, proteins, and lipids. So eventually, carbohydrates will be transformed into cellulose, proteins will be transformed into soluble protein, lipid will be transformed into threonine. So after some basic mathematical percentage calculation, the amount of cellulose that are going to enter is 1080 kg per hour, soluble protein will be 510 kg per hour, and threonine will be 30 kg per hour. So this can be summarized at the block diagram at the right hand side corner here. Is total of the biomass of cellulose, soluble protein, and threonine going to enter the reaction system for the production of biogas. So I will continue with the preliminary reactor optimization for our anaerobic digestions. So the left hand side here is the block diagram showing the arrangement of our anaerobic digester 1 and 2. And then the type of reactor that I'll be using is completely mixed digester after we done the ranking system for all type of digester. And then the reason we're using completely mixed digester is because this type of digester comes with a mixer, and this will ensure the proper agitation between our biomass and bacteria. And then also it comes with a heat exchanger and will ensure the temperature can always maintain at the desired temperature that we want. The CN ratio we set is 30. Temperature will be in the mesophilic range, 35 degrees Celsius to 45 degrees Celsius. Hydraulic retention time will be 30 days. And as we mentioned before, the number of stages will be 2 stages. They're showing here, CSTR, they're arranged in series. So the retention time for first stage will be 5 days. Retention time for second stage will be 25 days. So for the first stage, only including reaction for hydrolysis, acidogenesis, and acetogenesis. Second stage only for methanogenesis. The purpose we putting so long retention time for methanogenesis is because we want to ensure all the biomass can fully react with the bacteria in order to perform a more composition of methane of biogas here, because this is a methanogenesis process that's going to produce a very high purity of methane. And then the core digestions we're doing is pig manure mixed with sawdust that we discussed before, and also the total solid percentage will be 20%. So this is the overall reaction for anaerobic digestions. All of this we obtained from a ADMI book and also with online literature review. And then there are a total of 9 reactions. All these reactions will be set into ICON for the simulation process and also for performing the manual calculations. Okay, this is the flow sheet that we perform for ICON. Okay, and then now I will continue with the mass balance for our reaction system. So the assumption that we made first is the in equals to the sawdust plus pig manure plus with water the entering digester 1, and the out will be referring to the biogas 1 plus with biogas 2 with the liquid digestate. So the total icon simulation for in is 9000, total icon simulation for out is 9000.01, and the showing of a 0.001 percentage error. For manual calculation, the in is 9000 also, and then the out is 8936.65. This showing a 0.704 kg per hour. And I will discuss why there's a difference between icon and manual later. So the right hand side table showing the total biogas collected from biogas 1 stream and biogas 2 stream. So as we can see, the total collected for icon is 1736.04 kg per hour. Manual is 1635.77 kg per hour, and manual calculation showing there is a 6.13% lesser than icon calculations. And then I show you an example why. Because let's say for component water, manual they're showing 0 water coming out for biogas. It's because we assume there is 0 liquid going out from the gas stream. Means there's only gas in gas stream. However, in the icon, they're showing water coming out at the biogas stream also. That's why this will create a difference between manual and icon simulations. So, however, our team will be using icon simulation result to further perform the separation system calculation, because we believe icon is a more accurate type of calculation comparing to our manual calculation. And then this is all from me. Okay, thank you.
Hi, my name is Ang Lizi, and I'm going to talk about the separation system at our biogas production plant. So, the separation process in our biogas production plant involves the use of 2 water scrubbers, or also known as adsorption columns, to remove major impurities such as carbon dioxide and hydrogen sulfide from the biogas coming out of the anaerobic digester. Water scrubbing is a physical adsorption process, and thus no chemicals are required other than water. So now I'm going to talk about water scrubbing occurring in the first adsorption column. Liquid digestate flowing from a belt press separator flows into the first water scrubber from the top, while raw biogas with a methane mass percentage of 24.2% flows into the scrubber from the bottom. The first water scrubber has a theoretical stage of 10 and operates at a pressure of 3000 kPa or 30 bar. However, after undergoing water scrubbing, the methane mass percentage in biogas only increases to about 28.2%. Therefore, a second water scrubber has to be utilized to further increase the biogas purity to over 95% methane. Fresh water is used as a medium to remove CO2 and H2S in the second scrubber. Prior to entering the adsorption column from the top, fresh water is cooled to a temperature of 5 degrees Celsius. Biogas from the first scrubber enters the second scrubber from the bottom. Just like the first scrubber, the second scrubber has 10 theoretical stages and is operated at a pressure of 3000 kPa. After a second water scrubbing process, the final composition of upgraded biogas consists of 95.7% methane, 3.6% oxygen, and trace amounts of water and hydrogen. No H2S is detected in the biogas coming out of the second scrubber, indicating that 100% H2S removal efficiency is achieved. On the other hand, mass percentage of CO2 decreases from 69.5% in the raw biogas to 3.6% in the upgraded biogas, indicating a CO2 removal efficiency of 94.8% is achieved after going through the water scrubbing process twice. As a methane content of 95.7% is achieved in the final upgraded biogas, it is said to fulfill the standard natural gas quality and is qualified to be injected into the gas grid of Gas Malaysia. As for the wastewater coming out of both adsorption columns, they are sent to the wastewater treatment plant, operated by an external wastewater management company to be treated before being discharged into a river. In biogas upgrading, applying the technique of adsorption, the underlying principle is that CO2 and H2S are more soluble than methane in water. Raw biogas meets water that flows counter-currently in an adsorption column. Thus, loaded water leaving the column will contain increased carbon dioxide and hydrogen sulfide concentration, whereas upgraded biogas leaving the column will be enriched with methane. In this plant design project, two common adsorption techniques used for upgrading of biogas are proposed, namely water scrubbing and chemical scrubbing. To select a separation system out of these two, the advantages and disadvantages as well as estimated maintenance cost of each adsorption system are studied and summarized in Table 1 and Table 2. So, based on Table 1, it can be summarized that both water scrubbing and chemical scrubbing are able to produce biogas of high purity or high methane content, and also low methane losses. However, water scrubbing is a slower process as compared to chemical scrubbing, and it also requires a larger column volume due to the large amount of water needed to remove CO2 and H2S. Despite the drawbacks of water scrubbing, its advantages relative to chemical scrubbing is that it requires lower solvent regeneration energy. Its wastewater stream needs no special treatment, and it is easier to handle water than chemical solvent. Most importantly, water scrubbing requires relatively lower operating and maintenance costs of 15,000 per year compared to chemical scrubbing of 59,000 pounds per year according to Table 2. Therefore, in our biogas plant, water scrubbing is selected over chemical scrubbing to purify raw biogas coming out of the anaerobic digester. Next, I'm going to talk about the belt press separator, which is a type of liquid-solid separator used to separate digestate, a byproduct of biogas production, into liquid and solid digestate. In a belt press separator, water is separated from the raw digestate and then used as a medium to perform water scrubbing in the first column. Replacing fresh water with liquid digestate can cut down on the usage of fresh water and subsequently save costs for the plant. The solid digestate in which amount of water has been reduced from 95% to 27% can then be sold as a biofertilizer to generate a little extra income for the biogas production plant. In our project, three types of liquid-solid separators are considered. There is centrifuge, screw press, and belt press separator. The weight matrix method is used to evaluate the most suitable liquid-solid separator for the separation of digestate into liquid and solid digestate. The ranking system is established with a score of 1 for most undesirable or not recommended, and 5 for most desirable best option. So based on the weight matrix comparison in Table 4, belt press separator has the highest score. It has the lowest electricity or energy consumption, and hence can save electricity and cost. Since it has commendable overall separation efficiency, as it is ranked the second highest out of the three choices, the belt press separator is selected to be used in digestate separation at our biogas production plant. So that's all from me. Thank you.
In economic potential, we must consider EP1 and EP2, which is economic potential 1 and economic potential 2. For EP1, the formula is the product minus with raw materials. And as for the raw materials are sodas, water, and manure. Each of the price are stated in table 14. And from the market analysis, we found that the price of sodas is 0.035 ringgit per kg, and the price for water is 1 ringgit per kg, and for manure, we assume free from the farm. For the consumption of the year, we assume that there are 365 days per year, and time with the price of each raw material so that we can get the value of the cost. And from the table, the total cost of raw materials is 700,000. And as for products, the products are biogas and fertilizer. Each of the price are stated in table 14. From the market analysis, we found that the price of the biogas is 50 ringgit per kg, and the price for fertilizers is 2 ringgit per kg. So the revenue cost for biogas is 58 million, in the range of 58 millions, and for fertilizer, the revenue cost is 4 million, which make the total revenue of the products are 67 million in total. So to find the profit, the total revenue of the product minus with the total cost of raw material, and the profit will be 67 million. 32,943 of biogas production plant. And for EP2 is the revenue minus with cost material minus with utility, the formula. And for table 15 shows that the tariff rates for high voltage industry during peak and off-peak hour period provided by TNB. So the rate for peak hour is 33 cents and for off-peak is 20 cents. And table 16 shows the cost before the heat integrations. We have 2 coolers and 2 heaters. Before heat integration, the energy consumption for the coolers and heaters are 700 and 200, which make the total energy use is 900. Then in order to get the total cost in hour, the energy of each utility are times with the rate of peak period and off-peak period. And to get the total cost for a day, the total cost in hour is needed to times with 8 hours as for the peak period and 16 hours as for the off-peak periods. Then sum up the total of cost of both utility in a day, and we got 5,687 ringgit per day. Next, the total cost of both utilities per day have to times with year, which consists of 365 days to get the cost per year, and the amount is 2,776,000 ringgit per year. Table 17 shows the utility cost after heat integration. We still have 2 coolers and 2 heaters. After heat integration, the energy consumption for cooler and heater are 600 and 200, which are lesser than before and make the total energy use is 800. Then in order to get the total in hour, the energy of each utilities are times with the rate of peak period and off-peak period. And to get the total cost for a day, the total cost in hour is needed to times with 8 hours as for the peak period and 16 hours as for off-peak period. Then sum up the total and we got 5,200 ringgit per day. And the total cost of both utilities per day have to times with 365 in order to get total cost per year, and the amount is 1,900,000 ringgit per year, and that would make a 100,000 ringgit lesser. And in table 18 shows the summary of whole economic potentials which include EP1 and EP2. For EP2, EP1 is minus with the amount of before heat and after heat integration. So that's all for economic analysis. As for process flow diagram, figure 4 shows the process flow diagram before heat integrations, and figure 5 shows the process flow diagram after heat integration. So the difference is we added one heat exchanger to the heat exchange design. as we highlighted the heat exchanger with yellow color to make it clearer. And for heat integration part, the first step is the identification of hot and cold stream in the process. In this process, we have 4 streams, 2 hot and 2 cold, and mostly for the temperature is in the range of 5 to 45 degrees Celsius. And the heat load itself will extract from the icon software so that the CP can be calculated. In this chapter, we use HIN software to generate the heat exchanger network. And from figure 1, we obtain the information that we obtain from the heat cascade. And the minimum temperature difference is 10 because we found that it's suitable for biogas production. And the heating duties and the cooling duties are 200 and 674. From the cascade, the pinch temperature we obtain is 13. And from figure 3 shows that the optimized heat exchanger network, as shown in the figure, 1 heat exchanger and 2 cold utility and 2 hot utilities are added to the entire network for balancing, as the first heat exchanger is to connect between first stream and the third stream, which the amount of the heat load is 38 kilowatt. And for the second stream is fully done by utility, and the heat load is 42 kilowatt. And for the third stream at above pinch, it can be inserted only by cold utility, C4, which is 115 kilowatt, because there are no cold stream to be action, and same goes to the fourth stream, which can be only inserted with cold utility with the amount of 559 kilowatt. As for CC and GCC, CC is the composite curve and GCC is a grand composite curve. So composite curves are constructed from the diagram of the heat cascade. The hot composition curve is known as the heat source, while the cold composite curve is known as the cold source. The heat is recovered in hot composite curve and transferred to the cold composite curve. And the grand composite curve indicates the difference between the heat available from the hot stream of the process and the heat required by the cold stream of the process. And moving on to the comparison of utility consumption, this is the summary of utility requirement before and after heat integration. As you can see that the reduction of percent of hot utility are 5.4%, and for cold utility is 15.6%.
For the second part of my presentation, I'll be presenting on the piping and instrumentation diagram as well as the control strategies. So this is the P&ID developed by our group for our biogas plant design. For the control strategies, we will first discuss on the anaerobic digester and heat exchanger. For our digester, we will have 2 control objectives: to control the temperature of reactor and to control the pressure of reactor. So we'll be using feedback type of controls to manipulate the temperature of inlet stream and also to manipulate the outlet flow rate of digester. For our heat exchanger, we will want to control the temperature of heat exchanger outlet stream. So similarly, we'll be also using a feedback type of control to manipulate the flow rate of cooling water for cooler, or to manipulate the flow rate of steam for heater. So as you can see here, we have a board-mounted temperature transmitter. We send the electrical signal to our temperature indicating controller. And over here, we also have another temperature transmitter. We send the electrical signal to our controller as well, which then sends us a signal to our control valve to control the inlet steam for our heat exchanger. Over here, we have our pressure transmitter and also our pressure controller to control the pressure of our reactor. Moving on is our water scrubber, where we also have 2 control objectives. First is to control the flow rate of wastewater, and second is to control the pressure of water scrubber. So similarly, we'll be using feedback type of controls for these 2 control objectives. And we will want to manipulate the flow rate of outlet stream for wastewater for the first objective, and for the second one is to manipulate the flow rate of biogas produced. So as you can see here, On top, we will have our pressure transmitter and also our pressure controller to manipulate our outlet stream from our water scrubber. And for the wastewater stream, we want to manipulate the flow rate. So we have our flow rate transmitter and also a flow rate indicating controller. Next is our belt press separator, where our control objective is to control the flow rate of liquid digestate produced. Similarly, we'll be using a feedback type of control to manipulate the flow rate of liquid digestate. Then for our pump, we will want to control the pressure of the outlet stream. So over here we have a pressure transmitter, which measures the pressure of the outlet stream, and then it sends an electrical signal to our pressure indicating controller, which in turn sends an electrical signal to our pump so that we can manipulate the temperature or the flow rate of pump. For expander, it is almost similar to our pump, where we want to control the pressure of our outlet stream from the expander. So we'll be using a feedback type of control to manipulate the temperature or the flow rate of our compressor. Last but not least is our shell and tube heat exchanger. So as you can see here, our control objective is to control the temperature of inlet stream. We can do that by having a capillary tube send a signal to our temperature transmitter. The temperature transmitter in turn will send an electrical signal to our temperature indicating controller, and then send another electrical signal to our temperature transducer, which converts our electrical signal to a pressure signal. And then you will send a pneumatic signal to our pneumatic regulated actuator, which opens or closes the valve. So by doing so, we can manipulate the flow rate of inlet stream to heat exchanger. That's all from me. Thank you.
Now, moving on to the HAZOP, or Hazard and Operability Studies, which is used to examine the system and anticipate risk associated with the system. So from our P&ID, we have identified 7 key points on nodes, which are Node 1, Digester 1, Node 2, Digester 2, Node 3, Mixer 1, Node 4, Mixer 2, Node 5, Water Scrubber 1, Node 6, Water Scrubber 2, and Node 7, Solid and Liquid Separator. So once we have identified these nodes, we looked for parameters that might deviate in this node and the possible causes, consequences, and actions required that we might take to overcome this deviation. Now, looking at the digester 1 or node 1, the possible deviations might be temperature, pressure, flow, or pH, and the possible causes are related to malfunctions of components, pipe blockage, or leakage. So the consequences are mostly related to inhibition of bacterial activity in the digester, and the actions that we could probably take is properly maintaining the malfunction component whenever necessary, or installing control systems to ensure proper control over the digester. Next, moving on to digester 2, which is similar to digester 1, might also experience deviation in temperature, pressure, flow, and pH. The possible causes are also malfunction components, pipe leakage, pipe blockage, or improper flow of feed from digester 1. So the consequences are mostly interrupted digestion rate, disrupted product quality. So the actions that we could probably take are proper maintenance of malfunction component or installation of alarm system or control systems to monitor and control the flow of the digester. Moving on to node 3, mixer 1, the possible deviations that we have identified are pressure and flow, which could possibly caused by pipe blockage, pipe leakage, or malfunction sensors. The consequences are mostly related to the concentration of the feedstock or pressure buildup in the mixer that might lead to ruptures of pipe or the vessel itself. The actions that we could probably take is frequent maintenance of the malfunction component or installation of proper prevention systems. Next, mixer 2 is also similar to mixer 1, might also face deviation in pressure and flow due to similar causes, which are pipe blockage, pipe leakage, and malfunction components, which could be prevented by proper maintenance time to time. Next, water scrubber or node 5. The water scrubber might face deviations in surrounding temperature, pressure, or flow. The surrounding temperature is mostly caused by hot weather or cold weather and could result in low purity or loss of methane in the liquid stream. So the actions that we could probably take is to control the water flow rate, whichever relevant. And then there might be deviations in pressure and flow due to malfunction system components or improper loading rate, which could be prevented by using installation of pressure sensors and control system or maintenance of the malfunction component time to time. Water scrubber 2 is also similar to water scrubber 1, might face deviations in surrounding temperature, pressure, and flow, possibly due to the different loading rate or malfunction components or inlet blockages. It might lead to the flooding of material or impure biogas produced. So the actions that we could possibly take is install pressure or sensor and control system or maintaining the components time to time. Finally, note 7, represented by the solid and liquid separator, might face deviations in terms of pressure and flow, possibly due to improper loading rate or malfunction system or blockages in inlet. The consequences is that there will be undesired water content in the product, whether high or low, and this could be prevented by installing proper sensor and control system or maintaining the components from time to time frequently. Thank you.